Hi Science 10, welcome to our very last physics video on chapter 6, looking at mechanical and energy and how it's made up of a combination of potential and kinetic energy. So that's what it means when we say energy can't be created or destroyed. It's just being transferred from one type to another type. And when we look at mechanical energy, the energy of like moving parts, at any one time, whatever potential there is, you add that to whatever motion there is, and that's the total energy that contains, which is what we'll see in the following diagrams. That mechanical energy will not change. It's this within it, the potential and kinetic change in amounts. So when you have something with its maximum potential, if it's just staying in one spot with potential, it doesn't have kinetic yet. But as the motion rises, moves, as it moves, it's losing its potential. If you think of something like falling, as it moves to its maximum velocity and starts slowing down, that maximum spot or that maximum velocity would be the spot where it has the lowest potential. And when we look at this motion of the football, I think it's just more clear when we see an actual object moving that mechanical energy at all times is equal to the potential and kinetic together. So in the middle of its spot of motion, it will be pretty much where potential and kinetic are equal. When the football is at the like a split second that it's at the very highest that it will go, it's got maximum potential because it's got the greatest distance it can fall. But as it's falling, it is losing potential but gaining kinetic. It's going faster and faster just before it hits the earth. Just before, that would be the spot where it's got the maximum kinetic. When it hits the earth, then it's got absolutely zero potential when it's laying down on the ground. Okay, so in some of our equations, we may have to use this concept of the fact that potential energy and kinetic energy have to be added together to get your total of mechanical. The pendulum is often talked about when we look at potential and kinetic, where it stops. A pendulum stops, where you hold on to it before you let it go. That's maximum kinetic. When it's speeding at its fastest point, its lowest point here, it's maximum kinetic because it's fastest motion. When it goes up and stops again here, it's again maximum potential because it's stopped. Any place in its halfway between the max potential and max kinetic, you could say that potential energy and kinetic energy could be equal at that spot because it's halfway between the two maximums. And this example of the pendulum is looking at how the potential at the top is equal to the maximum at the bottom. And so what we're finding out here is a way to solve for one of the values that you don't have. And in this case, they're looking for what the velocity would be. And so if we find out our potential energy with an mgh at the top, where you read the information, it would be 1 kilogram times the gravitational acceleration times the height that it is at the top, then we can make that equal to the maximum at the bottom, where it's just fill in your mass in there, and you're just solving for the velocity. So to solve for the velocity, because they're equal to each other, you can see that our velocity there is going, we used our 4.905 joules as the, as you can see, we put it over here, as the energy in our second calculation. So because they are equal to each other at that halfway point, we can solve for velocity there, and it was 3.1 meters per second. So we can use the calculation for each of them to solve for something you're looking for. If we're solving for how high does she bounce in this trampoline example, you can see that we can solve for, this is just an easy MGH problem, and we're solving for H, so it's the 500 joules divided by mass times acceleration due to gravity, the 9.81. So this was an easy 1.5 solving for height in that question. And that brings us to the efficiency formula, where we're just looking at how efficient a system is by putting the output energy over the input energy times 100. And you'll find that these are pretty easy to do. We'll have some examples that I'll post for you to try out. But in this question, our input energy, if they state it in kilojoules, we just remember that we have to convert that to joules, so it's 8,700, and we'll use that for our input energy because that's how much he's using to run this race. And then to do an efficiency, we also need that output of kinetic energy that we're going to do with the half mv squared. So for that one, remember we need meters per second, so I just did a quick conversion of 50 kilometers per hour, divide by 3.6 to get 13.9 meters per second. So now we have everything we need to get our half mv squared. We've got our 80 kilograms here, and our velocity we just calculated when we divided by 3.6. So half mv squared, that will be the output energy, and we're just going to put the out over in times 100. So we calculated the out just now to be 7716. We calculated the input to be 8,700 in our first part of this question, and times by 100, and we get an 89% efficiency. Now, whenever you're doing these, it's kind of a trick to realize the smaller number will go over the bigger number. And if you're ever wondering, like, do I have the correct one? And that way, when you multiply by 100, the efficiency will still be under 100%, because we will never have an efficiency over 100%. So just remember, when you're doing efficiency examples and you're not sure which is the in or the out, always the smaller number over the bigger number is going to be a good hint to follow. For 6.2, just a really quick look at the environment and some of the efficiencies of different sources of energy, and it mentions that the car is about 20% efficient, which is kind of sad that 80% of the money that you spend on gas is not actually getting you anywhere. It is creating heat in your engine. But a light bulb, a regular screw-in incandescent light bulb, is only 5% efficient, so it's mostly 95% heat given off. So if you're using that light bulb to heat where your chicks are hatching, or your cat house or dog house or something, then you're using it for more of its actual better design, because it's actually giving off mostly heat. So we're looking at how much carbon dioxide, though, is released into the atmosphere when we burn fossil fuels. So we'll mention that again coming up here. But the little point here about energy conversions in a dam is talking about how the water at the top has a maximum potential, flows down with kinetic. At the bottom, it's got maximum kinetic energy, and basically the turbine is turned by the moving water with that kinetic energy, creating electricity. And in terms of fossil fuels, we're still in Alberta using 85% or 87% of our energy from fossil fuels, 47% from coal, 40% from natural gas, and a little bit of wind, hydro, biomass from other sources, 13%. So when we talk about fossil fuels, just like food, fuels contain chemical potential. So there's potential energy in the food and the fuel to do a work. I just put this little graph in here of how we're actually trying to phase out coal burning, though, because of the concern of the emissions in the greenhouse gases, carbon dioxide, among others, that are collecting in our atmosphere. So you can see that where we are right now, we're phasing out some of the coal plants and hoping that in the future we are by 2030 phasing out a lot of them, and depending on other sources of energy, for example solar energy or geothermal energy. So we'll keep watching for that. Nuclear energy, there's a little point about how there may be some advantages in that we don't burn fossil fuels and make those emissions, but the radioactive waste and the problems with where we dispose the nuclear waste are some huge concerns that we have not solved all the problems for yet, so we're not using that around here anyway a whole lot. Cogeneration, know that term, and it's when we are using that waste heat that some industry produces and using it for some good use, so warming the building or heating water or something else, so we're not just expelling hot gases or hot water and that being considered wasted energy. Okay, guys, that's a wrap for physics. A couple more review